Hello, in this video I'm going to go over how we can use various structures to create some sound effects for the Master System and the Game Gear. So on the NES and the Game Boy they have tone sweeps, and they also have like sound envelope commands to bend the volume of sounds over time and also switch tones of sounds over time. So what I'm going to go over here is how we can create our own on the Master System and Game Gear. So to start off with, this is going to visualize the two volume effects which I will now demonstrate in, bear with me a minute, I will just open this up in an emulator. Okay, so I'll go over this in a minute. So the first sound effect you're hearing here is using sound channel 3, just turning it on and off every couple of ticks to give us a plane noise for the engine in Sonic's plane there. Now the first two effects I'm going to go over here are using a volume sort of envelope or a sweep sort of structure which I've created here. So what it's going to do is it's going to play a sound using the system time number here as the frequency, and then the volume will then bend over time. So this is the first sound effect here. So you can hear it kind of warbling up and down over time. That's the first volume effect here. Now the second effect is this one. So the thing to note is what the volume is doing. As the sound goes, it kind of tweaks the volume up and down on this one. So that's the first two I wanted to cover there, and then I will stop this a minute. So what we were doing in the first one is, over the period of a few game updates, we rose the volume up and then stopped. So each time you hold down the 1 button, this sound effect will play, or rather this volume structure will work over the frequency that's being put out. So by creating an array structure, I will bring in some code now to try and back up what I'm saying here so you can kind of get an idea. So the first two volume effects are created using these const arrays here. So this is a quite simple way of doing it here. This is literally just volume values over a period of time that the sound's playing, and then this variable here holds the length of this array here. So then using the values in this array, we can literally just plug it into the volume command over time. So if I come down here a minute into the main loop here, so these are the volume commands here. So I've added two more commands to the sound module which I went over in the last episode, so we can dynamically change the volume whenever we want, and then another one to change the frequency. And what these commands will do is it will leave the channel's volume at that setting until you change it. So first off here we set the frequency to So this variable here is something in GBDK that's recording the system time. Every time one tick goes by, this value is incremented. So it works off the vertical blank, I believe. When one screen has been drawn, this then increments. So this is a 16-bit number here. So to convert that value into a workable frequency, we have to use this to mask the value so that it's always only between 0 and 1023. Then these variables here, vol and vol offset, are what I'm using to take the volume out of one of these volume arrays, and the volume offset is monitoring which byte is to be read each time. So as the program runs, the offset increments each time until it gets to the end, and then it turns off, as you can see here. So these are the two volume ones here which I've done. Don't know how that got out there. So to start off with, if you're holding down the one button, we plug in the frequency of the system time. We then read the next byte in the volume offset. Then we set sound channel 0 to the byte we've just gotten out of there, increment the offset value. Then if the volume offset is equal to the length of this array here, then we just set it back to 0 to start at the beginning again. So if you think of this as the volume over time, then you can imagine that you can put as much in here as you like to create all kinds of shapes. So you could have that, and then you could bung another one in there where you immediately drop it down, and then maybe take it up again, drop it down, and you can put as many sort of spikes as you kind of like in there. And then these jumps here will be between the last value and the next value, so you can pretty much just by putting in values between the minimum and the maximum volume range into these structures here, you can create your own volume envelope, if you like. So the first one is literally just raising the volume up, which is that one there. Over a period of time, it literally just goes up to the maximum volume, up to 15, and then pauses for 3 more ticks, and then ends. So by putting them into arrays like this, it makes them easy to kind of transport around. And then always make sure you put them as const arrays so that they go into ROM and not into RAM. And then the second one is this one here, where it slowly goes up over time and then stays at maximum volume for 3 ticks, and then the next tick it literally just plummets back down to 1. So if you keep playing that, then the sound will literally just jump around up and down, as it was happening in the example that I showed there. So I'll now go on to the other tone sweep. So we'll start this up again, and then using the D-pad I created different tone sweeps. So this one just sweeps up. It's using the frequency value as well. And then it does it for 26 ticks, and it's sweeping up using the value of 4. So if I use this effect is using the down button. So this sweeps down. There's 2 different stages to that. I'll show you that in a moment. And this is the last one. All of these are dependent on the value which is coming from here. So if the frequency in the tone sweep gets to either the minimum or the maximum value, then it literally just cuts off. Which is what you're hearing there when it has no range to play with. Now I will explain how this one works. So this one works slightly differently, the tones. So I'll move the code out first and then I will explain things here. So I'll bring this back briefly so you can kind of see this as I go here. So the first one here, each of these tone sweep settings needs 3 bytes. You could compress this down into maybe 1 or even 2 bytes, but for the demonstration purposes here, I've put them into 3 bytes to make it easier to work with. So the first is the change counter, or the tone steps as I've called it in code here. Basically it's how many times the last value here will be added or subtracted from the current frequency. So when you call the command, what it will do is it will take the current frequency, if you like, of the note that you plug into it. So let's scroll down here to kind of explain it properly here. So using the D-pads here, we can see what's going on. So this takes the first byte there, and then uses this here to plug in the array address into the tone data pointer. We then get the length of the array. We then record what the system time was in the frequency value here. So this could live in the sound modules if you wanted, or you could have a number of these for however many tone effects you might want to occur at the same time. So this value here, frequency, is what we apply the change value to every tick of the update. So when we set this, we first set the tone offset to 0. We then call load tone sweep. And then all this does is, using the tone offset, we first load the values that we're going to work with. So tone steps is how many times we're going to apply the number in the tone vowel steps. And then the second byte we read is the direction indicator. If it equals 1, then we make a note that the sweep is sweeping up. If it's 0, then we turn that to off. This allows us just to work with unsigned numbers, so we can have a greater value range. And then this is just printing stuff out onto the screen here. So the important bit is that we've tone steps, the data pointer, direction, and the value we want to work with are loaded from the array. So because we're loading it this way, we're also incrementing the value of tone offset as well. So by doing that, it means we can put in however many of these sweep effects in here. So I've only done a maximum of 3 here, but you could put in however many you want to change a sound wave over time. So the first value is how many ticks the frequency variable will be changed by over time. This is the variable we use here to plug into the sound channel. So if the sweep direction is 1, then this will get added with whatever value we have as the tone step variable. If it's 0, then this value will be subtracted from the frequency variable over time. And then once we've updated that frequency variable, we then plug that back into the sound channel to change its frequency. So where are we here? There you go. So set sound channel. After we've loaded the variables from the array, whichever sweep array we use. So you'll notice that the our sound channel commands for the tone sweeps are on channel 1, whereas the volume effects are on channel 0, and then the plain ticking engine sound is on channel 3. So you could have all of these different sound channels all doing something totally different over time, and then by just setting these commands here over time, we can play around with the tones or the volumes to create the various effects that we like. So all of these all of the D-pad commands, all they're really doing is these are the two important things here. All we're doing is loading the p-tone pointer and the length of the array into these two variables here, and then the start, how we set it all up, is exactly the same. And then each update, so we can only do one sweep thing at a time here. That's one of the settings that I did here, but you can obviously have a sweep variable for maybe each channel. It's kind of up to you what you kind of do with all this. In theory, you should be able to make all kinds of interesting sound effects, which is the implementation of what this video is all about, really. So a second bit that I wanted to go over here as well, which is kind of nothing to do with sound. Hopefully this all kind of makes some sort of sense. So this bit here is literally the sweep structure here, the change counter here. is literally, these are the variables you plug into each of the arrays. So this is the sort of variable over time, if you like. So the change counter, each of these individual sort of parts here would be one group of 3 bytes. And obviously the more changes you want to do on the sound envelope, the more of these you have to add to the array. And then the good thing about the these data structures is these tone sweeps here are totally frequency independent. So the effects that it actually carries out are dependent on the frequency value that you put in there to start with. So what you could do is create like a simple menu on here and then change the frequency, or play around with the change in the frequency value here, because this is depending on what you start with, depends what happens with the sound. As the sound is changed over time, it will stop if we go outside of the like the range here. So each update tone sweep is called, and then the frequency adds the change value, and then if it's greater than 1023, first we load the frequency back to that. We then increment the tone offset, and then this here will then tell us whether there's more bytes in the array or not. If there isn't, then the sweep is stopped, otherwise it loads the new bytes into the tone array and then calls itself again to redo it all. So the next thing I wanted to cover in this video is one of the things with sprites on the it's going to be more prevalent on the Master System than the Game Gear, is because each sprite's horizontal position only holds a byte. It means, I can explain it better with the demo here. If I open this up again. So these tiles here, they have an attribute to have priority over the sprites, which is why Sonic goes behind them. And then this is needed because if these are not there, then parts of the sprites prematurely disappear, because the horizontal position of the sprite is the same as the actual width of the screen. So you'll get an indication of this once he goes past this side here. He'll loop around to the top here. There you go, you saw it there, and then you'll see it again here, and then it will happen again. Now by blanking out, by putting the tiles at the borders, giving them this attribute here, so this here gives them a priority over the sprites. So by drawing those at the borders, it means you can have your sprites go outside of the borders and kind of be masked. I also did there's also an additional thing in this code as well to set sprite position 16. So what this does is this takes assigned short as the horizontal position, and then using that, it then automatically will clip the sprite. So this variable here holds the horizontal position of the sprite. So it checks to see whether it's outside of the screen, if you like, because it can only ever be between 0 and 255. And then if that is the case, then these parts here are set to tell the sprite to be put off the screen. So this is the draw part for that group of sprites for Sonic there. He's actually made of 4 sprites. If I bring that up, I'll this is a game I'm working on at the moment, which works nicely with the sound effects, which is they kind of needed each other really. So as you can see, Sonic's made of like 4 parts here, and then to animate him, I've literally just changed the front sprite here to the blade being rotated around, which is why there's this type here, group 4. So what this command will, what this check will do here is, if its horizontal position is between 0 and 255, if it's less than 0 or greater than 255, we hide the sprite by putting its vertical position off screen. Otherwise, we mask the bottom byte of the signed short we passed in, so that we only get the 0 to 255 part of it, and then put him on screen. And then the set position bit here does kind of exactly the same. So this is just the command to add the sprite group to the list using the settings here, which will put it off screen. So this is actually puts them all off screen here. I didn't realise that was there, so I'll change that now. And then this one here uses the 16-bit signed number here, and then each part of the group, it checks to make sure that it's on screen. If it's not, then it will hide it. Otherwise, it will loop around to the other side and cause all kinds of glitches. This is kind of the effect that we will need when implementing a scrolling game as well. If you have like a game which scrolls in all 4 directions, then obviously the actors need to move on to the screen via top, bottom, or left and right. But the top and bottom will probably be fine as long as your sprites aren't too tall. But because the horizontal variable that we have to hold the sprite's horizontal position can only be the same size as the screen, there would be no way to move them on in a decent sort of fashion. So that's all for this video here. Hopefully you'll find some use for it. Let me know if you managed to make some interesting sound effects. Okay, that's it for now.